lecture 6. This is lecture number 6. E5 local design. Yeah. So let's work on some of the basic of device physics. I will not go too much into detail, but just little bit about it. Same thing has been copied from Behzad Razavi, that is those figures. Or some of the explanation might be different. So it's with my experience, so I'm talking about. So generally, if this is a device, which is what you have made is this is an NMOS. If I apply here gate voltage, source is grounded and drain is 0.1 volt. If this is the case, what's going to happen if I am going to give some potential over here? Then you will have negative ions over here, right? Other side. And when you keep on increasing, so this was one concept, by the way, but this is not the complete picture. The complete picture is as follows. If you are going to give voltage over here, other side you will have the negatively charged ions which are depleted mode. Understand this is negative but depleted. This means depleted one, and these are fatty and they are immobile, by the way. These which are over here, these are immobile. This is the symbol for immobile, whereas other sides are the channel charges which are actually mobile, which does not have this circle. So in that case, when you are increasing the voltage, this side, so first of all, you do not have these charges, so do not consider these are here. When you keep on increasing, other side is keep on increasing this the depleted mode or immobile charges over here, and definitely same number of plus, right? So this is like a capacitive, two plates are there, one side you are giving the plus, so other side keep on going minus. However, as per the device device physics, this is going to happen, and at one point of time when this is fully occupied with these immobile charges, there is something called channel which will have start building some charges which are mobile by nature. So it keep on increasing. By the way, when the first charge is coming here, which is mobile one, that is the point when you are going to observe the threshold voltage. This is the definition of threshold voltage, right? And when you keep on increasing, you will see that there is a path between drain to source, and whatever drain is there, so it can it can be supplied other side, or you can use it as an amplifier, you can use it as a switch, so depending on the other things. But what we are talking about is about the capacitance model. So if you look at this, the upper side of this device is actually the oxide capacitance, depending on Tox, which is thickness of the oxide. We are calling it oxide because this is metal layer, this is oxide layer, and this side is P substrate, is a semiconductor, and that's how it becomes MOS, right? This must be known to you already, N type or P type, but those MOS are there, right? So this is because of making between metal and oxide. This particular capacitance we are calling it oxide. Same way, the capacitance between this and this, like what it has been made over here, it's a C depleted capacitor because it's in the depletion layer. So that capacitance is there, right? So this already device, I'm not going into the detail of right now those parasitic capacitors. Those are also there, by the way. Those are also known as overlap, COV, overlap capacitors. Although this is okay, like in your cadence simulator or any simulator, it might happen that you can call this one as drain and this one also source, and same way you can do this one also. But this is illegal. Please do not do this. Don't do it in schematic ever. Okay, it's illegal. Why? Why we are not going to do this one? Geometrically it's same, right? But still we are preferring this only as source. It can be like depending on the voltages, right? You can change the direction. There is no problem. It's all about the model which has been given to you by the foundry, where overlap capacitances are not uniform. Overlap capacitance between states, source, uh, capacitance between gate to drain and gate to source are different. They may not be same. So model wise, whatever has been defined, it is with respect to this source. So it is expected you should not do change in schematic like source to drain and source to, like, that is not okay. It will give you wrong results. However, in layout you can do that. In layout there is no problem. There are no model. Those are the actually pictorial things, and it's going to give you capacitances depending on how much overlap and other things you are creating. So in layout it's okay. You can do that. You can change the source to drain, drain to source, and depending on the voltages, the current direction will also change. Right? So now, if this is the case, you must have studied something called. Have you studied anywhere CV characteristic in your device course? CV. So let's study that if you have not studied. By the way, this particular configuration is known as the MOSCAP. This particular configuration is known as the MOSCAP, where I want to see my NMOS transistor or EMOS transistor as capacitance, right? So in that case, if this is the configuration where gate is connected to a positive voltage with some frequency, so like this, I'm applying here V in, let's call it A sin omega t, and other side I'm connecting drain, source and body together. So there are two plates. One side is this side is one plate and this side is one plate. This overall thing is known as the gate to body capacitance. This is gate and this is body. So CGB with respect to VGS needs to be plotted. So let's plot that. Let's try it. All device physics people, they are teaching this. You have not studied device physics? Have you studied? What's your name? Girl. Pragya. So Pragya, you haven't studied device. What is your BTech in electrical or electronics? Electronics. You studied, right? You studied this plot. No, no. MTech you have started just, right? So your university needs to be change your syllabus. It's a very important plot. This is being taught, right? Every college. Then make the plot. If you are not studied, then also like with the knowledge I gave you, it will be easy to plot the the CGB versus VGS. you are increasing VGS, how does it look like? If VGS is less than V threshold voltage, let's go this way. If VGS is less than V threshold voltage, what's going to happen? Note that in this case, you need to take care of overlap capacitances also. I know that there are various capacitances. CG, let's call it CGD, CGS, right? There must be a big capacitor. COX, right? C depleted. Let's not take this one. This is a little smaller. So what will happen if I am going to apply 0 volt over here? If it is 0 volt over here, what's going to happen? What capacitance I am going to see? Why? But why? I don't see COX either, right? It's not there. So what is the rule to have the capacitance first of all? First of all, you should have some frequency. Okay, this frequency I am applying. No problem. Let's assume that it's 1 volt sine omega t with frequency of 1 megahertz I am applying. Then, but A is actually, sorry, A is equal to 0 volt. That is what I am applying, right? So it's almost as good as DC, right? And other side is also 0, so 0. So there is no voltage difference between two plates. There are no capacitance, ideally. Until the point when there is a VTH, I should not see any capacitance because it's as good as, there are no, building of capacitance ideally. However, if you have seen the last one where these immobile charges are created in the depleted mode of region. So depending on the difference between this plate and this plate, note that, by the way, generation of these immobile charges, although it is drawn over here like this, however, it's not like that. If you are applying here some voltage over here, so voltage, if it is here, if you are saying positive over here, the immobile charges are near to this ground, understand? It cannot be near to this one, this area. It has to be near to this one because this is the energy conservation law. If you are giving positive from here, then same negative has to be supplied from here, right? That's the physics. If it is not there, then so in principle it has to be near to this ground area. And if you look at the difference between the positive plate and negative plate, as you are giving less number of charges at the initially, so you will see that the difference between these two plates are far, and later on you will see that it's increasing, it's going other side, right? So capacitance is getting increased because the difference between these two plates are getting decreased, right? So if I am drawing this not in ideal case, it has to be like this, right? And when it reaches the value which is more than threshold voltage, again you can see the channel charge is there. So it will also create a bridge between drain to source, but it will take some time. So before threshold itself, there has to be one value. Let's call this one as VTH1. Before exact threshold, in between, this capacitance should keep on increasing, right? And that will be the drastic change because the charges are coming in the channel, right? By the way, in this particular region, when you are there, when the charges are getting built up in channel, that particular mode of operation we are going to call it sub threshold conduction. right? So that is sub threshold conduction, where your transistor is not in inversion mode, exactly not in inversion mode. However, that is also known as inversion, but the name of that one is weak inversion mode. And other side, when it build up all charges, it becomes strong inversion, and after the value of voltage, I should get all the capacitance activated, including overlap. So CGS plus CGD plus COX, C depletion if you want to add, which is little bit smaller. So you can add all these, right? Any problem with this? Right? No problem, right? So this is how it should look like. But note that what we have studied, it has one catch. The catch is this frequency of operation has to be low. If you are keeping very high, then such charges cannot be trapped so much fast, and you can't see this capacitance. So actually, if it is very high frequency, and I am keeping this to you people to find out, the capacitance will not change. If you find out, or you find out how the capacitance will look like, can you keep it in like assignment number 1? You just write down how this low frequency and high frequency capacitance curves will look like, and I would recommend you please find out this in cadence and submit. Okay, so along with your so I'll take one exam where these plots might be asked in assignment exam. However, you have to plot this also in cadence. Okay, so the next term they can do it, right? Hmm. Okay, so you please plot that, but low frequency and high frequency, you need to find out what will happen at low frequency, what will happen at high frequency. And believe me, it's not easy. It's not easy. I'm not going to give you the trick over here. Okay, so you just find out how to find out capacitance with respect to voltage. Okay, so this is not the normal one. This is CV curve, not IV curve. IV, I believe that you know, so I'm not going into IV curve and other things, right? So this is one thing. What will happen other side? That is more interesting. So generally we are studying with following. So what are the different region of operation for a MOSFET? Let's say a very simple one, cutoff. Then triode. It has also another name called linear because its characteristic is linear. Okay. What else? Saturation. Saturation has also another name, inversion mode of operation. Right. This is also there. Just now we have talk about it. So combiningly both of them, weak inversion and strong inversion is known as saturation. But in principle, strong inversion equal to saturation, and weak inversion is equal to sub threshold. Okay, this is very popular field of study, sub threshold conduction based circuits. This happens when you are at very low frequency application like ECG, EEG, or biomedical application, where it's very difficult to achieve the required inversion voltages. So then you might be working in subthreshold. Maybe with time when you are going to work on it, you will understand it's the requirement of subthreshold. Right? Yeah. Okay, what else? So these are already there. What else is here? Hmm? That is very far. Okay, let's not go till breakdown. Breakdown is also there. True. Deep triode. So that goes to weak inversion. Right? That's not mode of operation, right? That's the second order effect. So another one is called accumulation. That is very rare. Device people are teaching this generally. We do not touch that. We do not require that. We make sure that our device is not in accumulated mode. We generally keep it, or we prefer to have it in, sorry, not weak, strong inversion or saturation mode of operation. Right? We want this. But while drawing the curve, there is something called Fermi potential. If you are going below Fermi potential, it is generally 130 nanometers, so 1 volt, minus 1 volt. So if it is that, then it's act like a, you know this whole thing will act like, transistor again, act like a, it's in strong inversion. So here actually it's this is larger than this side generally. So this is around, so minus 1 volt for 130 nanometer technology. This is around, let's say, 300 millivolt, something like that. I would recommend you please plot the, you know, uh, plot the MOSFET, then you will understand how does it look like, right? So let's keep this, in your kind of your lab experiment as well as the assignments first question. Okay. Okay. I'm so again. I'm not going into this IV characteristic. You must have studied this IV and all, right? So we are not going into that. I'm going into, the deeper into the analog side. This is no problem, right? Okay, let's try this one. By the way, these mosque now what we are doing, it's not given in any book. Okay? We are doing with, you know with some fun mode. So what will happen if you are keeping, the MOSFET in this, where gate is connected to VDD, so it's always in on mode. How the capacitance curve should look like? So this is Cx, and with respect to ground, that's why I'm calling it Cxp. Body is still ground, so everything with respect to ground, how the capacitance will look like. If I apply here 0 volt, what's going to happen? Of course, frequency is there, but so 0 volt, what's going to happen? Or near to 0 volt with some frequency, so some 1 millivolt or something like that. So how much capacitance you should see? Look, gate is already there. It's VDD supplied with VDD. There is a capacitance. There is the capacitance. There is a big capacitance with respect to ground, Cox, CGS, CGD. In principle, I should see all the capacitance, right? All capacitance will be there. It has to be Cox plus CGB plus CGS. So as I keep on increasing this voltage, one point of time where I am reaching VDD minus VTH, till that point there is no problem, right? Till that point the transistor is in saturation mode of operation. Understand, right now this part is saturation mode or the strong inversion mode. When I am increasing now a bit from VDD minus VTH, this capacitance is keep on decreasing and follow what actually we have studied in the previous one. So it's a reverse one. Are you following? Okay, if you follow, then can we try this one? Let's try this one. So CGB. Understand this is PMOS. This is also known as MOSCAP, by the way. This is MOSCAP. Earlier was also MOSCAP, but generally people are using such kind of MOSCAP. This one and the first one, which you have said, the reverse one was like kind of my invention, you could say. So what will happen if I am applying 0 volt over here or near to 0 volt? This is PMOS. This is PMOS. How PMOS will work? This is PMOS. It's reverse one. I'm again not drawing. Let's find out. If you are not able to find out, you use Cadence or maybe Simica or maybe LT Spice or anywhere where you can draw the characteristic. You just look at that. Maybe just for fun, you can try this one also. If you like this one, then you can try this one also. You can alternate also. You can add few more. Right. So let's keep this one in your assignment number 1. Please prepare that and keep these questions. Okay. So you find out. So I told you the trick how to find out the capacitance stuff. You can discuss with other friends also or whatever. But this is not readily available in any book. It's not available in any book. Maybe in some papers might be available. Okay. So this was about CV curve. These are very important because this will give you, understanding of many things in future while designing the circuits with MOSCAP. Anyway, so region of operations are as follows. We already talked about it: triode or linear weak inversion mode or strong inversion or the saturation. Other modes are also there, but let's assume that we are not keeping a transistor in that, or we are not interested, considering the fact that we are interested in amplification or we want to use it as a switch. So in that case, if you are in digital course, you are keeping your transistor in triode or linear, or as a switch you are in analog, which is amplified. So both the way you are going to work, but the equations are changing, by the way. The ID equation will change, right? So governing equation in all the cases, like weak inversion, strong inversion, everywhere the equations are different. Okay. So this is again like just for completeness. Right after the IV characteristic or the IV equation derivation, you can have this equation, by the way. Once you derive it, you will see that when you are in triode region or in linear region, your device will govern by mu and C of W by L VGS minus VTH times VDS minus half VDS square. This is the equation. Remember it forever, because this is the equation we are going to use it for entire course or mostly all the courses of VLSI. This is the main equation, governing equation. You don't have to remember other things, but this equation, if you know, then there is no problem, right? So this is one thing. And other, okay, so it will look like this one. So it is not drawn intentionally, with slope, but actually it is with slope, right? This is happening with channel and modulation. We'll talk about it maybe in later slides. So this is the equation when it's in linear, and linear is very important when you want to design a circuit where your transistor act as a switch. So when it is an act as a switch, or it will act as a resistance, the value of resistance determined by the slope of the characteristic, by the way. Okay, so this slope. Name of this transistor is R on. When I'm writing R on, it's well understood that it has to be the switch resistance, R on or R off, nothing else. Understand, there is one more resistance should be coming in this particular region. I'm not talking about that resistance, I'm talking about the resistance which is actually in the triode region. The slope of this characteristic should give you the resistance R on. And how much R on do you expect, by the way? Low, high, or low? You want low resistance. How much low? So anything less than 1 kilo ohm. Okay. So sometimes you might be able to achieve good resistance. Sometimes you won't be able to achieve good resistance. Some people are keeping, very high W. If you are keeping very high W, then resistance is very low, right? But you need to find out those trade-off, that how much W is required. Sometimes some people are also using something called transmission gate. In that case also the resistance is getting reduced because two devices are in parallel, right? But transmission gate does not have just only one reason to use it, but there are many other reasons. One of the reason is having the low resistance in that, right? So this is the equation which is going to govern this. Note that in this particular equation you are not going to see the name called VDS set, because many people are using or they like the word VDS set. That is reserved for saturation mode of operation, when your transistor is in saturation. So that is VDS set, or some people like it to call that one as VOV. So that is VOV is V overdrive voltage, right? Some people are also writing VOD also, right? So there are different notation, but that is reserved for different mode of operation, right? Yeah, tell me.
So VOV and VD set
Yeah,
you
different books are using different notation, right? If you are using Rabe, they are using VDS set. Digital course everywhere it has VDS set, but you don't work in saturation mode. That's why this equation will be used. Okay. So this is the determine the equation of the NMOS triode using a drain current equation. What I asked. This is for NMOS only. What I wrote, I made some mistake or okay. I'll think about it and I'll discuss this class. Oh, okay, I understand. So basically, if you remember last time when we talked about device side, so these are another thing. What they are doing is they call that when transistor is in saturation or other mode of operation, it's depending on the threshold voltage how it's changing. So if it is more than 2 phi f, where phi is again a voltage or potential, right? And F is for Fermi. So Fermi potential 2 phi f, that makes the transistor is in saturation. So those notations are there. These are again for device only. So if you don't remember, there is no problem. But these are just for completeness. So, or you can say that when VDS is much lower than 2 VGS minus VTS, but these all these numbers are depending on the value when it's depending on the technology specific. These are the number. So we might not follow these numbers when you are going in 3 nanometer or 7 nanometer. So I am not going with that. But the whole thing is, if you have to find out the equation when it's in saturation mode of operation, then this is the equation which is going to follow, which we are writing also. And for the case when it's triode region, this is the equation. These two equations are there. So if I want to find out, okay, in this case, if I want to find out R on, can somebody help me to get the R on, value of R on? Hmm? How to find? Differentiate ID with respect to what?
VDS.
Hmm?
VDS.
Why VDS?
Because of slope. How long?
Because the plot has, we want the slope of that, so del ID by del VDS is going to give me the R on, and that's the R on voltage over here. So you can find out. Hmm? Sorry, 1 by R on. True. 1 by R on. Right. R on inverse. And in this case, by the way, this equation is actually very simpler. However, it is known as the square law equation. This is also another name of this equation. It is very popularly used in many books. Square law equation. Square law equation has L prime over here. Some books are following just L, some books are following L prime. I believe that L prime is the correct thing, which is actually the exact length, right? So that's the channel length. Mu and Cox are the model parameter, right? Now we understand what are the DC model parameters are mu and Cox and VGS minus VTS square. So if you make the derivative of this one, what will be the answer? Del ID with respect to VGS. There is no VDS, by the way. In this equation, there is no VDS. And whatever the characteristic has been drawn over here, in that it is constant. So there is no effect of VDS after going into saturation mode. That is the meaning of this plot, right? But that's the ideal plot. This is an ideal plot. In reality, such things won't happen. So if I am doing del ID by del VGS, if you remember when we have found out that two-port network, del ID by del VGS is defined as GM or the transconductance. So what will be the value of GM with respect to VGS? Hmm? Mu and Cox W by L, VGS minus VTS. You can also call it K and VGS minus VTS, right? Anyway, so you can keep it somewhere in your mind. Whenever it's required, you can use this equation, you can make the derivative. But this is not the whole picture. In reality, we are going to see this one. So we are going to study this when we are going to study the second order effects. In reality, the plot will look like this one. Yugal,
Sir, actually,
no. You cannot come inside them, right? There is no point.
so you said that without asking.
That is like 5-10 minutes here, they're fine.
Because of Janmashtami, sir.
So Janmashtami is like, we are not here for Janmashtami.
Sorry, sir.
You can leave, please. Okay, so the characteristic will look like this one, where it has some slope. This particular thing is known as the channel length modulation. This is happening because of channel length modulation. There are many other things which we are going to talk, but after maybe next lecture we are going to talk about it. That channel and modulation, body effect, and many other things. In a device, not in device perspective, but in a circuit perspective, how it's going to change the equation, because using channel and modulation, this equation will change and it will have some extra terms will be coming. So those terms will be added and that will change GM. That will also change, you know, RDS. Sorry, I should keep this RDS. When you make the derivative, so then you can find out this slope, which is 1 by RDS. So that can be also found out, and that's also channel and modulation resistance. Those things we are going to talk maybe on the next class. But for completion, let's go with the two-port network revisit. So it has these equations. If you're following, you can find out the fact that gate current is zero. That's the main reason why people are using MOS, right? Because gate current is zero, and you can say that input impedance is infinite, right? So if you derive the two-port network or small signal model, it look like this, right? So this is the small signal model you always have to remember in your mind. Now let's go this way. What is the impedance looking into gate terminal? Infinite. Into drain. Hmm? How much? Why 1 by GM? I don't see anything. I see 0. Infinite, right? Okay, sorry, not 0. Infinite, right? Because there is 0 current. So infinite impedance. Through source, what I'm saying. By the way, VGS was 0, that's why GM is going 0. Okay, those who are not able to see. So from source, 1 by GM. Last time I made one small mistake. If you're looking into this BJT, where one RPI is there, so looking from here is RPI. This one is RPI in shunt with 1 by GM, and this is again infinity. So one small problem was there. I told output impedance is infinity, no problem. Input impedance is RPI. However, I was saying RPI is infinity, but its value is not more than 1 kilo. It's lower value. So input impedance is low actually, not high. That was the mistake from my side. So RPI is much lower than 1 kilo ohm. So I confirm it, and that's why this becomes CCCS, current control current source. This is not voltage control current source, but it is current control current source. And looking into this, input impedance is infinite and output impedance is also infinite. So that makes voltage control current source, or you can call this one as OTA. When you are going to use it as an amplifier, it will be acting as an OTA. What is OTA? Operational transconductance amplifier. Transconductance is the one where output is current and output is current, right? And input is voltage. So current by voltage is going to give you the transconductance. So it's operational transconductance amplifier which you can design with this. However, with the use of BJT, it's going to give you the current amplifier, right? To make it voltage amplifier, you need to do lots of things. You need to add, the input stage, output stage, many things are there. That is what done in 741 as well. So if you study that, you will understand there are lots of things which are added just to make sure that it becomes voltage amplifier. Okay. So any doubt in this till now? So it was just revising the things or connecting device and circuit. Now it will be mostly circuit. Just few things I am going to talk about, which are channel and modulation, body effect, all these things, which are little bit of